How to add a soft reset to a D flip-flop. Welcome to the Digital VLSI interview prep channel. Here you'll find the most frequently asked questions. So if you like the content, share it with your friends and don't forget to like and subscribe. If you want access to more of these kind of questions, then use the link in the description and head over to my Udemy course below. Thank you. Let's walk through this problem step by step. So let's come up with a D flip-flop first. That should be a first and preliminary step to solving this problem, right? And then we will think about how to add a active low soft reset capability to the D flip-flop that we come up with. So a D flip-flop, as you guys know from previous videos, a D flip-flop looks like this. So there is a 2 to 1 mux with the enable pin, and as long as the enable is 1, the D will get passed through and latch into the flip-flop and therefore will reflect at the output of the D flip-flop. If the enable is 0, then the value of Q, the previous value of Q, will continue to show up at Q for every for every clock cycle, right? So in short, that's how the D flip-flop will work. And then this is the symbolic representation of the D flip-flop. It has basically 4 pins. Let's start with the clock. 2 inputs. One is the D input, another one is the enable input, and then one output, which is Q, right? So now that we know that, let's talk about how we can add an active low soft reset to this D flip-flop. For that, let's start with a simple table that indicates how the inputs and outputs should behave. So when the reset value, which will obviously be an input to the D flip-flop, is 0, then the D input is a don't care because the output has to be forced to 0, right? When the reset value is 1, then the output depends on the D input. And this is assuming the enable is 1, right? I wanted to keep the table here concise, and so I have not added another column here for enable, and thereby increasing the number of possibilities in this table, right? So let's just assume enable is 1 for all these combinations, and so therefore, if that's the case, the output will get reflected if the reset value is 1 based on what the input is. If the D input is 0, the output will be 0. If the D input is 1, the output will be 1, right? Okay, so now that we know that, you can maybe pause the video and try to modify this D flip-flop circuit to add an active low reset. So this is essentially how you would do it, right? It's a pretty straightforward way of doing it. So basically, you just insert an AND gate in between, and whenever the reset is active, meaning it's 0, irrespective of what D is, it will end up forcing a 0 into the flop, and on the next rising edge, the flop will latch a 0, and thereby forcing the output Q of this D flip-flop to a 0, right? This is a pretty straightforward way of adding or forcing the input of the D flip-flop to a 0 and thereby forcing the output to a 0. But let's continue. Let's use the original D flip-flop and try to modify it for that functionality, right? This is the original D flip-flop. This is the symbolic representation of the D flip-flop. This is what we came up with, right? But then, is that the optimal solution or the best way of implementing this active low soft reset? No, it's not. Why? Because doing this way, what that means is we need to put a mux in front of the AND gate, right? But if we do that, it will not be logically equivalent anymore. And what I mean by that is this circuitry can no more be represented by this dotted line because we have sort of modified it. If you have a pre-existing module, you always want to do whatever modifications you want on the outside, because that way, if you want a D flip-flop in this case that you want to use without the soft reset capability, then you can use it. But if you want to use a D flip-flop with a soft reset capability, then you just have to add some additional circuitry at the outside so that you have both the flavors available to you. Once you modify this D flip-flop on the inside, then you lose your access to one of the two flavors. And this is the modular thought process that you have to develop if you want to be a really good designer, right? So keeping that in mind, this is not the best approach. So let's see how we can modify this to make it modular and also adding the soft reset capability in the best way possible. So what we need to figure out is, in a nutshell, how do we force a 1 through this select line, which is the enable, when the active low soft reset is, when the active low reset is active, and transfer a 0 to the flop. Those are the two criteria we got to meet, right? Let me repeat that one more time for you. We need to figure out when the soft reset is active, meaning when the soft reset is 0, how do we force a 1 through the select or enable pin, and how do we force a 0 to the input of this flop, right? So what I would recommend is please pause the video and draw it out, because you need to add two simple logic gates at the enable and the D input of the D flip-flop, and you should be good to go. So when you guys have a diagram, come back, unpause the video, and try to compare what you came up with what I'm going to show. Okay, so here's the final circuit, right? This is the original D flip-flop. We haven't touched it, so you still have access to the original D flip-flop flavor that we have. But if you want a D flip-flop with a active low soft reset capability, then you just add these two gates outside, and now you have another access to another flavor of D flip-flop, right? So as we said, whenever the soft reset is active, meaning it's 0, we need to force the select or enable line to 1, and you simply invert it and add a OR gate. Thereby, whenever the soft reset is active, you force a 1 into the enable pin, and you force the data to a 0. Now how you do that? You just simply add a AND gate over here at the D input, right? So the data is one of the inputs to the AND gate, and the active low soft reset is the other input. When the soft reset is active, the output of the AND gate is automatically going to be forced to a 0, which will get propagated and get captured by this flop here, and thereby forcing the output of the D flip-flop to a 0. So I hope that makes sense, and you guys now understand how to convert a normal D flip-flop to a D flip-flop which has a soft reset capability.